I will continue discussing the exponential law. It is a very important one, and anyway there are so many aspects that there may be some repetition also, but does not matter. So, we said that for example, I have been giving the example of a fuse which does not show the wearing house effect, wearing out effect, and similarly a jeweled bearing, you have them in watches. So, there is no wearing out effect on such components, and they are good as good as new while they are functioning, right. So, it does not matter how long they have been functioning, they are as good as new, and if a fuse has not burnt out, it is like a new one. Jeweled bearing does not wear out. Okay. So, this is again and again I am trying to give you examples of components which and therefore, for such components the exponential law is appropriate and is supported by empirical evidence. Okay. That means, when you have collected data for such components, how long it takes for them to fail and so on. So, then and then fitting the curve to the data, it turns out that exponential law is an appropriate one for such components. Okay. So, another way of saying that there is no wearing out effect is as follows. Consider the conditional probability that capital T, the lifetime, lies between t and t plus delta t, given that capital T is greater than t. Right. Now, the intersection of these two events is simply this, right, because here also t is greater than t and it is less than t plus delta t. So, therefore, the intersection of these two events is this. So, then the conditional probability can be written as probability of the intersection of the two events divided by probability that t is greater than t. Right. Now, this you can see immediately is the probability t less than or equal to t plus delta t minus probability t less than or equal to t. So, this event, right, and since this is 1 minus e raised to minus alpha t plus delta t minus of 1 minus e raised to minus alpha t. Right. So, the 1 cancels out and you will be left with e raised to minus alpha t minus e raised to minus alpha of t plus delta t divided by this probability, which is e raised to minus alpha t. This of course, I am showing you for the exponential law. So, therefore, this is 1 minus e raised to minus alpha delta t, which is nothing but the probability that t lies between 0 and delta t. So, this tells you that this probability is independent. So, this conditional probability is independent of t, depends only on delta t, that is depends only on the length of the interval that you are considering. That means, you want to consider. So, that means, here from t to t plus delta t. So, the length of the interval is delta t. So, this probability, this conditional probability is independent of t and depends only on delta t, right. So, therefore, this is another way of saying that it is memoryless, or the wearing out effect is not there. That means, it is not it does not matter for how long the system has already been working, but now when you want to look at the probability that it will be working in the interval t to t, that means, it fails before t plus delta t, then that is dependent only on delta t. So, this is the whole idea, right. And so, we have seen that there are many situations where this is a very appropriate law. Now, see, just want to make a note here that even though this will also, this probability will also, if you say t less than or equal to capital T less than or equal to t plus delta t, this will also come out to be the same as this one, right. But since we are considering the conditional probability that t is greater than capital T, so therefore, we have to consider this event, right, and not this event. So, sometimes inadvertently maybe one can I may have written it like this, but when you are looking at this conditional probability, then it has to be t strictly less than capital T, and here it is less than or equal to t plus delta t. So, that would be the right way to write the event, and even though because of the continuous case the two probabilities may come out to be the same. This is the important part. So, thus as long as the component is working, it is as good as new. Now, in this equation, suppose I expand the right hand side. So, expansion for e raised to minus alpha delta t, right. So, all of you should be familiar that much calculus everybody has done. So, you can write down the expansion for e raised to minus alpha delta t, which will be 1 minus alpha delta t plus sorry, there should have been 2 factorial and so on powers of delta t. Okay. And then when you open up the brackets, 1 cancels out, and then you have alpha delta t plus higher power terms containing powers of terms like delta t square, delta t cube and so on. Fine. Now, when delta t is small, we can just ignore these terms, and therefore, for small delta t, probability of failure in time delta t is proportional to alpha delta t. Okay. So, this is what, again just reiterating what we have been saying. So, now in fact, we have given it a better expression from here. This is more you can immediately conclude quite a few things from here. So, that means, in a small interval, no matter where that time interval is, length delta t is, the probability of a failure in that time period is proportional to time period itself, delta t. Okay. Now, this is if you again see, I am saying the same thing again which I said. So, this is nothing but your Poisson process. This is one of the basic assumptions of a Poisson process. In fact, what you can say now here is that, suppose you have a electronic device and you have lot of components which have the same which follow the same exponential failure law, and they have the identical distribution, that is the same parameter lambda, let us say, right. And then you are and of course, the components behave independently. So, that condition also for a Poisson process is satisfied, that is the arrivals are independent, and so here the components will behave independently. So, their failures will also be independent of each other. So, with that assumption plus the assumption that in a small interval the probability of a failure is proportional to alpha delta t. Okay. So, then in that case, with those two assumptions, you can then say that if you are considering let us say time period 0 comma t, then the number of failures within this time interval will follow a Poisson process. So, you can see that the arrival and the inter-arrival times that we will talk in detail later on. So, the inter-arrival times and the arrival pattern. So, inter-arrival times would be exponential, and the arrival patterns would be Poisson, and so on. So, we will continue with that discussion. Now, because again we want to say this thing now, that since the for the exponential failure law, the failure behavior of an item depends only on the length of the time period being considered and not on its past history, right. So, therefore, and for the non-exponential, just like we have so far considered the normal failure law. So, for non-exponential failure laws, the past does matter, it does matter, because when you are under stress, then the wearing out effect is there, and so it depends on how long the stress has been, and so on. So, for non-exponential failure laws, the past does matter. So, therefore, it is important to understand that when you talk of the time t, life length. So, for the exponential failure law, t will denote the time in service up to failure, right, because it does not matter when you start counting. It is if the component is functioning, then you start counting the time from then. So, up to failure, t will denote the time, it does not matter when you start counting it, right. But for non-exponential components, t will denote the total life length up to failure. So, you started functioning from whatever time you count your time from that, and so capital T will, in that case, the normal the random variable will denote the total life length up to failure. So, total means that whenever you start service or whenever you start using the item, then you start counting your time from here, whereas here it does not matter, you start counting from any point and then up to failure. So, the life length will denote that. So, t will denote that time period. So, it is important to understand these two the differences between how you count the time for exponential failure law and for a non-exponential failure law. Let us look at the various graphs connected with the exponential failure law. So, this is a familiar one, right. At t equal to 0, this will be 1, it will be equal to alpha, right, and then it will go down this way, right. As t goes to infinity, this will go to 0, and then correspondingly see z, your failure law rate of failure z t is alpha, right, which is a constant, right, and so it continues to be alpha, value alpha for all values of t. This is your t axis, this is your z t axis. Okay. Then f t would be, of course, so what f t would be what, 1 minus e raised to minus alpha t, right, sorry, this function, right. So, 1 minus e raised to minus alpha. So, at t equal to 0, this will be 0, and then as t goes to infinity, this goes to 0. So, the function finally goes up to 1. Okay. And then your R t, the failure function, or sorry, the reliability function, yes, the reliability function R t, which is 1 minus f t, and therefore, this is equal to e raised to minus alpha t. And so, here again at t equal to 0, the value will be 1, and then it will go down as t goes to infinity. So, the reliability goes down as t goes to infinity. Okay. So, this is the graph for the PDF of an exponential failure law. So, at t equal to 0, it is equal to alpha, and then it goes down to infinity as t goes to infinity. Then we know that the failure rate z t, or the hazard function, this is a constant, right, and the constant value is alpha. Then the cumulative density function, which is f t is equal to 1 minus e raised to minus alpha t, would be again at t equal to 0, it will be 0, because this will be 1. So, 1 minus 1 is 0, and then it goes up to 1. The reliability function would be e raised to minus alpha t. So, at t equal to 0, this will be 1, and then again it goes down to infinity. Okay. So, these are the 4 graphs that you, or the 4 functions that you relate with the exponential law, and you have a picture of the all 4 of them. Okay. Now, let us look at this example. If the parameter alpha is given and reliability is also given, that means R t is specified, we can find t. So, that means given alpha, that means you have specified the failure law, and then you are asking for a certain level of reliability. So, you want to know what would be the time required for the equipment or the component to operate to achieve that reliability, right. So, the number of hours of operations required for the specified reliability level, I should say. Okay. Now, let alpha be 0.01 and reliability is 0.9. So, you want this to be obtained, and your parameter is 0.01. So, if alpha is 0.01, then your mean will be what? So, for an exponential distribution, the mean is, so expected t would be 1 by alpha, which is 1 upon 0.01, which is 100 hours. So, if you are talking, if your unit of time is hours, then this is 100 hours. Okay. So, now, so therefore, the number of hours that are required is given by to achieve this reliability level. Then you are saying that e raised to minus 0.01 t. Remember, this is the function, reliability function. So, e raised to minus 0.01 t should be equal to 0.9. So, you want that value of t, which will satisfy this equation. So, you take log of both sides, and this will then give you minus 0.01 t is equal to ln of 0.9. And remember, ln of a number less than 1 is negative. So, therefore, this is okay. So, there is a minus sign here, right. And so, if you now divide by 0.01, then you get that t is equal to 100 into ln of 0.9, okay, which comes out to be, if you look up the values of ln 0.9, then multiplied by 100, that gives you 10.54 hours. So, therefore, the way you can interpret this is that out of 100 components, if all are working simultaneously, and 90, what we are saying is, and if they all operate for 10.54 hours, then our expectation is that 90 of them will not fail. So, after 10.54 hours 90 of them will be working. So, this is what we mean by the reliability level and so on. So, therefore, so essentially it is a question of given what and then what you can compute. So, sometimes you may be given the time, then you can compute the reliability level, right. So, if you are given t, then you will be able to determine this number, and if you are given this reliability level, then you can determine the time, or if you are given time and reliability, then you can determine the parameter. That means you can uniquely determine the exponential failure law, because you only need the parameter alpha to determine the failure law, exponential failure law. Okay, let us look at another example. So, here you are given the cost C in terms of mu. So, C is 3 mu square be the cost of producing an item, where mu is the mean time to failure. So, again we are talking of a exponential distribution, exponential failure law, and mu is the mean. So, therefore, if mu is the mean, then remember the distribution, the failure law would be minus 1 by mu t, right. This is what you have. Okay. Now, so the cost is 3 times mu square. So, which means that if mu is small, then the cost is small. If mu is large, then your cost would be accordingly large, right. Okay. Which makes sense. So, maybe because if your mean time to failure is small, then you expect that the cost is also small, and if the mean time to failure is big, is large number, then that means you expect the component not to fail very early or has a long lifetime, and in that case the cost of producing that item would be also high. So, it is reasonable to assume the cost in this way, right. Now, suppose rupees d are earned for every hour the item is in service. So, you earn a profit of d rupees for per hour when the item is functional. Okay. Now, you want, so therefore, profit per item is given by, the profit would be d into t, if the lifetime is t hours, then d into t minus the cost 3 mu square, right, and t is the number of service hours, right. So, find the value of mu for which the profit is maximized. So, expected profit. So, certainly because this is a random variable, so we will maximize the expected profit. So, the expected profit is this, right, because d of E t, this is the, I mean this is not a random variable, this would be some fixed number. So, then d of E t minus 3 mu square, and E t is mu. So, therefore, d mu minus 3 mu square. So, exactly what I was saying that, yeah. So, this is so therefore, to maximize this expected profit, I would differentiate this with respect to mu, it is a function of mu, and put it to 0. So, that gives me d minus 6 mu equal to 0, which implies that mu is d by 6, and of course, only critical value, and but still you need to verify that d square by d mu square is of the function is minus 6, which is less than 0. So, therefore, the critical point is a point of maxima. So, the value that we get of mu here is a value which maximizes the expected profit. Okay. So, therefore, mu equal to d by 6 is maximizing the profit, and the maximum profit is d square by 12 rupees. Okay. So, just trying to give you a feeling for the failure law, exponential failure law, and the kind of problems that can be discussed and that arise corresponding to this. So, again the level is at a very basic, the level I have kept is very basic, because this is just trying to give you a glimpse of how these probability tools that we have learnt can be used for answering so many questions about day to day operations of systems, service systems, and so on. So, this is the whole idea, right. Otherwise, reliability theory has become very complex, and in fact, the next failure law that we will discuss is a complex one, and we again will just try to understand the basics of that of the weibull failure law. So, let us now I will talk about the weibull failure law, and you can see that Now, the degree of complexity is going up, and okay, we have not so far discussed this distribution probability law also. So, let us look at it, and the idea here is to because the constant failure rate was only applicable to a special kind of components which were not let us say, for which there was no wearing out effect, right. So, that was a special situation, and we have seen that there are so many almost electronic devices are behave that way, and so the exponential law is appropriate for them. So, now if we want to modify this constant rate, then the weibull failure law was thought of, and this is alpha beta t raised to beta minus 1. So, now you have introduced power of t of the time, and of course, 2 parameters, and there can be more than 2 also. So, we are talking of a 2 parameter weibull failure law, and so here alpha and beta are positive and t is greater than 0 as usual, because it is the lifetime variable. So, therefore, has to be non-negative. Now, you can look at, I have drawn various pictures of z t when for the values of beta and different values of alpha and beta, and so maybe we will just look at it. Let me just first compute your f t. So, remember we said that we can compute f t uniquely given the failure rate functions z t. So, then this is z t e raised to minus integral of 0 to t of z s d s, integral 0 to t of z s d s, right. This is our formula for computing f t given z t. So, then here if you substitute for z t, this is alpha beta into t raised to beta minus 1 e raised to minus integral 0 to t alpha beta s raised to beta minus 1 d s, right. So, if you just look at this integral, let us just compute. So, this will be s raised to beta minus 1 d s from 0 to t, and the integral here is 1 by beta s raised to beta 0 to t. So, therefore, this is 1 by beta t raised to beta. So, if I make that substitution here, I get my f t as this. So, this is the PDF connected with the weibull failure law, and the failure law is specified there. So, yeah, the way it looks, it is a little complicated, but just see, when you put alpha equal to 1 and beta equal to 1, alpha equal to 1, beta equal to 1, then this is 1, and this will be e raised to minus t. So, e raised to minus t would be your yeah. So, this would be your PDF, right, the exponential with parameter 1, and that is the one I have drawn here, right. Then if you look at the value alpha equal to 1 and beta equal to 2. So, therefore, in this case the for beta equal to 1, this will be exponential, and the failure rate will be constant, which will be 1. So, beta, of course, here I have drawn it only for beta equal to 1. So, alpha is as it is. This one is, of course, you put alpha equal to 1 also. So, anyway, this is your function for the failure rate. Okay. Then when you put alpha equal to 1 and beta equal to 2, then I have drawn this one. This is the one for beta equal to 2. Of course, not a very accurate, not very accurate figures. So, you can always Google search, and then you can find nice pictures, very accurately drawn graphs. Okay. So, beta equal to 2. Now, you look at this thing here. This is alpha 1 beta equal to 2. So, this is twice t, that means it is a linear function of t. So, therefore, you see for different values of beta, things are changing. So, alpha equal to 1 beta equal to 1, you got constant, alpha equal to 1 beta equal to 2, you get and in fact, any value of alpha does not have to be 1, then in that case it will be a linear function of t, right, if beta is 2, right. And so, here of course, I have drawn it for alpha equal to 1 and beta equal to 2, the diagram. Then and the corresponding PDF will be 2 t e raised to minus t square. Okay. Then for beta equal to 3, for example, I have drawn the picture here also for beta equal to 3. So, then this starts taking a bit more bell shape, and beta equal to 3, alpha equal to 1 will be 3 times t square. So, that will be, that means that t is a quadratic function of t. Okay. And correspondingly your this thing will be, so here when beta is 3, then of course, this is t square and then e raised to something, right. So, quadratic into exponential function. Now, and for beta equal to 5, for example, it will become more steep like this, and then as beta goes to infinity, you see you can show that it will simply be a spike, just a spike, because beta is going to infinity, sorry, I mean, yeah, if beta is going to infinity, then this will simply just spike into this thing, which you call as a delta function. So, at the point, yeah. So, somewhere here it will become a spike as beta goes to infinity. Yeah. So, the thing becomes narrower and narrower as your beta goes up. So, here beta is the shape parameter, therefore, you see beta is the shape parameter and 1 by alpha is the scale parameter. So, you scale the whole thing, right. That means, when you are drawing the thing, then you. So, failure rate is proportional to power of power beta minus 1 of t. So, therefore, this is the generalization that we have made to the constant failure rate, and so this is the failure rate is now proportional to t raised to beta minus 1. Okay. So, you can see that, yeah, and then this also gives you a good feeling. Now, for example, if your beta is less than 1, if beta is less than 1, then this will become negative. So, t will be in the denominator, and so alpha beta upon t raised to 1 minus beta, and that will be for as t goes to infinity. So, the denominator will go to 0, and therefore, this will let me. So, okay, alpha beta upon t raised to 1 minus beta, right. So, as t goes to 0, this goes to infinity, the denominator t goes to 0, this goes to infinity, and so no, it should be the other way. I want to show that for beta less than 1, for beta less than 1, this is negative. So, when I take it here, it will be positive, this power is positive, and so as yes, as t goes to 0, this goes to infinity, because this goes to 0. So, this goes to infinity as t goes to 0, right. Yeah, that should be no. And therefore, it is this way, and then as t goes to infinity, this goes to 0. Okay. And so, failure rate decreases with time. Now, failure rate decreases with time, that means, see, essentially defective items fail early, and the failure rate decreases over time as the defective items have been weeded out. So, all the defective items have been weeded out from the population. So, that case the failure rate will decrease with time, right. So, all defective items fail early, and therefore, as time progresses, your failure rate will decrease. So, this is the situation that gets modeled when you are by putting beta equal to less than 1. So, all values of beta between 0 and this thing here, right. So, if you take this, then this is the situation it will supposed to model, and beta equal to 1 we have already discussed thoroughly. Now, here of course, since the failure rate is constant, so as time goes on, the failure rate does not change. So, this is because random external events are causing the failure. That could be one of the reason. So, random external, for example, if a fuse will blow out if the high current comes suddenly in the line, right. So, therefore, that is an external event, and many others can be explained, high wind and so on. For other high tension wires you can snap and so on. So, therefore, beta equal to 1, because the failure rate is constant, it is understood that external events would cause the failure, could be the reason for the failure. And for beta greater than 1, as we have seen, failure rate is increasing with time, and therefore, this models the situation where aging process has a role to play in the failure of the system. Okay. And that is parts are likely to fail as time goes on, and this is when the stress part. So, you see this certainly captures, it is a more complex and little more comprehensive failure law, which captures more than one situation. Okay. and you can play around by manipulating the value of beta and alpha and try to get accurate results. So, this is the whole idea, and we will continue with the discussion on weibull distributions. So, let us make this computations about the expected value and the variance of a weibull distribution. So, E t, the theorem says that E t is alpha raised to minus 1 by beta, gamma of 1 by beta plus 1. So, we all know the gamma function, and then V t, the variance would be alpha raised to minus 2 by beta, gamma of 2 beta plus 1 minus gamma of 1 beta plus 1 whole square, right, which is we are using the formula that variance is E t square minus expected value of t square minus expected t whole square, right. Now, so just apply the, because we have already computed the f t, the PDF for t when t has a weibull failure law, then this is t into alpha beta t raised to beta minus 1 e raised to minus alpha into t beta dt, right. Okay. So, yes. So, now you can see that this t beta minus 1 and t beta. So, this prompts you to make the substitution that t beta is y. So, we will do this. So, again you are all familiar with this part of the calculus, you can do this integration. So, t raised to beta is y, that will make beta t raised to beta minus 1 dt is equal to dy. The limits will not change, they will remain from 0 to infinity. Okay. Since beta is positive, so for t equal to infinity, y will also be infinity, and t 0, y is 0. Okay. So, now therefore, this thing whole thing gets replaced by dy. So, you have a beta t beta minus 1 and dt. So, this we will replace by dy. Then you are left with a t and an alpha, and then e raised to minus alpha y, because t raised to beta is y. So, therefore, this is what you have, alpha e raised to minus alpha y and y raised to 1 by beta, and there is a So, y raised to 1 by beta, because you have a t here. So, t will be y raised to 1 by beta. Okay. So, therefore, this is what you have. Now, you see this looks familiar, because you can now relate this with the gamma function, gamma PDF. So, here alpha e raised to minus alpha y, then you have to have alpha y here as the variable. So, alpha y raised to 1 by beta. Now, y 1 by beta is there. So, alpha 1 by beta I am adding here. So, therefore, I will divide by alpha 1 by beta, and then I need a gamma of 1 by beta plus 1 for this integral dy to be 1, because this is the PDF of a gamma distribution with parameters alpha and 1 by beta. So, then I am left with this and this final. So, therefore, the expected value of the random variable t, where t has a weibull failure law, is given by gamma of 1 by beta plus 1 into alpha raised to minus 1 by beta, right. Okay. And then the second part should be straightforward. So, you have this. So, therefore, I need to compute expected value of t square, and so it will be t square alpha beta t raised to beta minus 1. So, now you see your again beta t raised to beta minus 1 and e raised to t raised to beta would become this thing. I am sorry, I mean beta t raised to beta minus 1 dt, that will be dy from here, right. And then you have a t square. So, that will be y raised to I mean I have not written the integral here. So, anyway, this will reduce, this will be equal to 0 to why have I written t, this is 0 to infinity, this will be 0 to infinity. So, y raised to 2 by beta, and then you have an alpha, and then you have e raised to minus alpha y dy, right. So, here again I will do the same trick that I did here. So, alpha e raised to minus alpha y is there, then this you need to write this 0 to infinity alpha y raised to 2 by beta alpha e raised to minus alpha y, right. It is exactly the same thing, and then you will divide by alpha raised to 2 by beta, then you need a 2 by beta plus 1, right, and you will multiply by 2 raised to beta by gamma of 2 beta plus 1, 2 by beta plus 1, and so this whole thing will be and there is a dy, right. So, then you will be left with gamma of 2 by beta plus 1 into alpha raised to minus 2 by beta. So, this is the expected value of t square, right. and therefore, the variance will be this minus the expected t whole square. So, you take out alpha raised to minus 2 by beta common, and then you are left with this. So, this is just for your now, and here again we could make use of the gamma distribution computations to compute the expected value and the variance. Now, again, so we have seen that weibull distribution represents an appropriate model for a failure law whenever the system is composed of a number of components, right. Okay. And the failure is primarily due to the most severe flaw among a large number of flaws in the system. So, this is what is happening. So, you have lot of components and lot of parts in the device that you are using, and each one of them has a flaw, but then it will be governed by the most severe flaw among all the components. This is what the you can say that this is the representation of a this is a situation which a weibull distribution will represent, and your alpha beta, and of course, you have seen that by changing the values of beta, you can either have an increasing failure rate or a constant failure rate or a decreasing failure rate. So, this we have already seen, right. And yeah, so here just being able to give you a short glimpse into the what this distribution can do, and one needs to really work at a lot of examples to understand the implications or the importance of this distribution. Okay. Now, let us just look at this example. So, each of the 6 tubes of a radio set has a life length in years. So, our time unit is a year, which may be considered a random variable. Okay. So, the lifetime of a tube in a radio set in number of years should be considered as a random variable. Suppose these tubes function independently of each other. Okay. So, that is important. They are working independently of each other. What is the probability that no tube will have to be replaced during the first 2 months of service? Okay. So, we will have to translate this to years, because our unit of time is in years. Now, the PDF of the failure time to failure is given by this 50 into t e raised to minus 25 t square. So, immediately you can recognize that this is a weibull distribution, and since t has power 1. So, your beta is 2, right. This is beta is equal to 2, because t raised to beta minus 1. So, therefore, if beta is 2, then alpha is, and of course, from here alpha is 25. So, this is alpha beta into t raised to beta minus 1 e raised to minus 25 t square, because this is beta. So, this is the weibull distribution, right. Now, of course, we have not made this computation of the for the weibull distribution, but certainly you can do it, or maybe you can use numerical methods. So, essentially yeah, it is a weibull distribution with these are the parameters. Then you, since the tubes are functioning independent of each other, and you do not want and of course, let me say that your t is 1 by this is 2 months. So, 1 by 6, which I have written. Okay, I have written it here, right. So, t is 1 by 6, you want to your capital T, right. So, yeah. So, we want, there are 6 tubes, they are working independently of each other. We do not want any one of them to fail. So, therefore, in the first 2 months. So, the probability of, let us say, the first tube not failing in the first 2 months is T 1 greater than or equal to 1 by 6. So, time unit is 1 by 6, and then since all of them are independent of each other, we do not want any of them to fail. So, then this would be probability T 1 greater than or equal to 1 by 6 raised to 6. So, this we will this is not a difficult integral, again because see, you have seen my computations here for E t and variance t. So, you can just use those, you can use the gamma distribution computations to do the computations here, and then you can find out this probability, raise it to 6. So, the answer is approximately 0.5 raised to 6. Okay. So, this integral you can handle now, since I have given you the method of computing E t. So, exactly it just boils down to that for different values of t and so on, right. Okay. So, now this does not exhaust the failure laws. I have only, as I told you and I have been repeating it, that we are only considering very basic failure laws here, and my of course aim was to, since we have discussed the probability theory and so the various tools you have learnt about. So, I just thought that I would like to show you the various applications also of these tools that we have learned in the course. So, that has been the whole whole idea, the theme across the course, that you learn the theory and then you learn to use it also. And so, Markov processes, discrete Markov processes, then we have talked about continuous Markov processes, and in the process special cases which are Poisson and exponential distributions, and then birth and death processes, and finally, applications to reliability theory. And here also the basic concepts have been given to you, but as I said, it is a very growing, large growing area, very important, and a lot of applications of course probability theory, and there are many more people have come up with failure laws, which probably supplement the theory that has been discussed here. Okay.